If the distance time graph describes the motion of an object across a period of time, the velocity time graph shows the velocity of an object over a period of time. In a velocity time graph, time is represented on the x-axis and velocity on the y-axis. Look at this graph. What does it tell you about the movement of the car? The graph tells us that the car's velocity increased uniformly from 0 to 25 meters per second in 100 seconds. Graphs are useful because they allow us to infer a variety of information from them. A distance time graph tells us about the distance covered by an object during a span of time. It also allows us to deduce the speed of the object during a given time interval. Similarly, a velocity time graph informs us about an object's velocity during specified periods of time. An object's acceleration or retardation pattern over a period of time, and its displacement during a specified period of time. Let's examine a velocity time graph and understand how it can be used for these calculations. The car begins its motion from rest and acquires a speed of 90 km per hour in a period of 100 seconds. This graph depicts how velocity increases over a period of time. From this graph, you can find the velocity of the car at any given point in time. For example, at 100 seconds, the velocity was 25 meters per second. Note that this graph shows velocity in meters per second. Do you remember the conversion from kilometers per hour to meters per second and vice versa? Here is a quick recall of the conversion. To convert a value from kilometers per hour to meters per second, multiply the value by the factor 5 by 18. And to convert a value from meters per second to kilometers per hour, multiply the value by the factor 18 by 5. Shown on screen are a few converted values. Now look at the graph again. You can see here that the car increased its velocity from 10 meters per second to 20 meters per second in a span of 40 seconds. The change in velocity of an object in unit time is called its acceleration. Acceleration is calculated as the difference in the final and initial velocities divided by the time taken. The initial velocity of the car at 40 seconds is 10 meters per second. And its final velocity after 80 seconds is 20 meters per second. The acceleration of the car in the 40-second time span can be calculated like this. Now, here is a velocity time graph of a train accelerating from 0 to 15 meters per second in 20 seconds. Calculate its acceleration between the 12th and 20th second. The acceleration in the 8-second time frame can be calculated like this. A velocity time graph can also be used to calculate the displacement of an object in a specified interval of time. Let's calculate the displacement of the car between the 20th and the 60th second. To begin, let's draw perpendiculars from the x-axis to the velocity time line for the 20th and 60th seconds. The area of the quadrilateral ABCD will give us the displacement of the car. How will you calculate this area? This irregular figure can be divided into a rectangle and a triangle. By adding the areas of the rectangle ABCE and the triangle AED, you can calculate the area of the quadrilateral ABCED. You can calculate the area of the triangle AED like this. Now you can calculate the area of the rectangle ABCE like this. Hence, the area of quadrilateral ABCED is 400, which is the displacement of the car between the 20th and 60th second. These velocity time graphs showed that the car and the train increased velocity uniformly with time. Their graphs are hence a straight progressive line beginning from the origin. Such graphs depict that the object is experiencing uniform acceleration. This car is moving at a constant velocity. Its velocity time graph appears like this. Now look at this distance time graph for a given object. What does each of these graphs show? The straight line on the distance time graph depicts that the object is at rest. The distance remains unchanged over a period of time. The straight line on the velocity time graph depicts that the object is moving with a constant velocity. With the passage of time, it covers a certain distance, which can be calculated using the graph. The area of quadrilateral ABCD will give us the distance covered by the car from the 20th to the 70th second. When the velocity of an object does not change uniformly with time, its graph describes an irregular shape like this. Such a velocity time graph depicts non-uniform acceleration. When an object uniformly reduces its velocity in a given period of time, it is said to experience uniform retardation or deceleration. This graph represents a train experiencing uniform retardation as it reduces its velocity from 15 meters per second to 0 in 20 seconds. Its displacement at any interval of time can be calculated by constructing a quadrilateral and calculating its area. Just as we did when we calculated the displacement of the car in uniform acceleration.